Hey, in this tutorial we're going to be looking at a review of differentiation. So the gradient of a curve is the rule for the instantaneous rate of change of the function. So the gradient of a curve is the rule for the instantaneous rate of change of a function. Okay, so differentiation by first principles. Okay, so we'll probably remember this from our studies in year 11. Okay, you would have seen a diagram like this before. So if we've got a point x, okay, then we also have a point, okay, which would be f of x, or if you like, y for that x point. But we say, well, it's our function at the point x. Okay, we also have some point a bit further along from x, which is x plus some value h, and h is just a constant, so it could be, we've added an extra 1 to it. Okay, then we also have the point f of x plus h, where we've subbed x plus h into our function f of x. Okay, if we draw a line joining those 2 points, okay, we get a secant, okay, going through those 2 points, and we also have drawn our tangent, okay, at our point x. Okay, so we can see that our blue line here isn't that close to our tangent. However, okay, if we moved our x plus h value across, so if we made h smaller, then we'd have a line that's in between here. Okay, that would match closer. If we made h smaller, we get closer again, and h smaller again, we get even closer. Okay, that's the idea with our first principles. So, just think about though, if we were to work out the gradient of this line here, well, it's just rise over run. So it would be y2 take y1, okay, so f of x plus h take f of x, over x plus h take x, okay, for our x2 take x1. Okay, so subbing that in, we get that. Okay, that we have f of x plus h take f of x over x plus h take x. And we just simplify that a little bit because our x's are going to cancel out on our bottom line. So we'll get f of x plus h take f of x over h. Okay, so that's our rate of change of our line here. Now to actually get our rate of change for our tangent, or our gradient of the tangent, what we're doing is we're going to use the limits. So basically we say the limit as h approaches 0 of this stuff will give us our gradient function, which we use f dash of x. Okay, we use a little dash when we talk about our derivative function. So basically we're saying as h approaches 0 here, then we're going to get the gradient of our tangent. Okay, and we'll get to looking at that, how we use it right now. Okay, so we've got a worked example, which is using first principles, find the gradient of the tangent at x equals 2 for f of x equals x squared plus 5x plus 6. Okay, so we know what our f of x is, so remember our equation is f dash of x equals the limit as h approaches 0 of f of x plus h take f of x over h. Okay, so we've got to sub in all our parts. So we know what f of x is. It's here. But we need to work out what f of x plus h equals. Okay, so remember wherever we've got x in our function up here, we're going to put x plus h. So we're going to get x plus h squared plus 5 times x plus h plus 6. Okay, so that's going to be our f of x plus h. Okay, so we can now build our equation here. So I'm going to say, well, f dash of x is equal to the limit as h approaches 0 of our f of x plus h, all this stuff, now x plus h squared plus 5 times x plus h plus 6, okay, minus, I need to do this in brackets, f of x, our x squared plus 5x plus 6. Okay, so just make sure that you are always putting your f of x in brackets, otherwise you're going to take away our x squared, but you'd add 5x and add 6, where really we need to take them away from all our steps. And all that is over h. Okay, so we need to expand out our brackets. Okay, expand our brackets here. We're going to get x squared plus 2xh plus h squared plus 5x plus 5h plus 6 take x squared, take 5x, take 6, all over h. Now we can collect like terms and such. So we have the limit as h approaches 0. Okay, well we have x squared take x squared, so they're going to cancel out. Okay, we've got 5x take 5x, so they're going to cancel out. And we've got 6 take 6, so they're going to cancel out. So we're left with, at the moment, 2xh plus h squared plus 5h over h. Okay, so what we do now is we take h out as a common factor. So we have the limit as h approaches 0 of h outside at 2x plus h plus 5 over h. Okay, now h's can cancel out. Okay, you're left with f dash of x equals the limit as h approaches 0 of 2x plus h plus 5. Okay, once we've simplified it as much as possible, okay, you'll remember from our limit work last year that to actually do this part, what you do is you just actually let h equal 0. So that means then, I'll just come over here, that f dash of x is equal to 2x plus 5. So once you simplify it as much as possible, you let h equal 0, okay, and you'll be left with other things all the time. Okay, you just got to be careful, don't jump in too early with letting h equal 0, because otherwise you're going to have a 0 on your bottom line of your fraction here, which means it'd be undefined. So you just got to make sure that you don't do it too early. Now, we haven't actually finished answering the questions. Okay, we found the gradient function for our tangent here. Okay, but we've got to do it at x equals 2. So then we just need to go f dash of 2 equals 2 times 2 plus 5, which is going to equal 9. Okay, look, this is something that can pop up on the exam, usually just in a multiple choice question, but it is something that you need to make sure that you're able to do. So we'll keep moving on. Okay, so we had the derivative of x to the power n. So if we have some function, f of x equals ax to the power n, so a is just a constant, n is just a constant, then the derivative is equal to nax to the power n minus 1. So remembering, okay, the way this works is we bring our original power down the front, okay, and reduce our power by 1. Okay, and we just need to say where n and a are an element of all real numbers. Okay, so remember, for our polynomials like this, bring our power down the front, reduce our power by 1. Okay, if we have two functions, if we have a function, f of x defined as two functions added together, so g of x plus h of x, then our derivative is simply the derivative of g of x plus our derivative of h of x. And similarly, if we have f of x equals g of x minus h of x, then f dash of x is going to equal g dash of x minus h dash of x. So we have a couple of worked examples here that we'll go through. So we want to differentiate these. So we've got f of x equals x cubed, take 1 on 2x, plus 4. Okay, so what we want to do here is just simplify these a little bit and say that we've got x cubed, take a half x to the negative 1 plus 4. Okay, and the easiest way to do, the reason why we do that, is just so we can see what our power is on our x down the bottom there. So now we can just use our rule here. So f dash of x, okay, our power comes out the front, so 3x, reduce our power by 1, makes it 2. Bring our power down the front, so negative 1 times negative a half will give us positive a half x to the power of minus 2, because we've got to take 1 away. Okay, and if we have a constant, that just disappears. Okay, so our 4 just drops away, and we can rewrite this as 3x squared plus 1 over 2x squared. Okay, it's always best to write your answers with positive powers of x, so in this case that means put on the bottom line. Okay, our next one, got a little bit of work on this one. Okay, so we've got f of x equals square root of x, take 3x cubed on 4x squared. Okay, so what we're going to do here is say, well, f of x is equal to square root of x on 4x squared minus 3x cubed on 4x squared. Okay, split into our two fractions. Our square root of x, remember that's x to the power of half over 4x squared. Take 3x cubed on 4x squared. Okay, what we're going to do is we can cancel out our powers here. So remember we subtract our powers. Okay, so we can say that we've got x to the power of, well, a half take 2 is negative 3 on 2 on our 4. We've got to keep our 4 there. Okay, and again we can subtract our powers. So we can say take 3 on 4, well 3 take 2 is just 1. So 3 on 4x. Okay, so then f dash of x, okay, well our power has to come out the front. So we have minus 3 on 2 times x to the negative 5 on 2 on 4. Okay, and then minus, well our power is 1, so our x disappears and just leaves us with 3 on 4. So f dash of x is going to equal minus 3 x to the negative 5 on 2 on 8 takes 3 on 4. Okay, and so that means that we can write, I'll just come up here, okay, that we're minus 3 on 8 times x to the 5 on 2, okay, take 3 on 4. Okay, so a little bit more work to do with a couple of these ones. Okay, again, we just put our power as a positive power of x. Okay, if you wanted to, you could also say that f dash of x was equal to minus 3 on 8 times the square root of x to the 5, take 3 on 4. You could also do that. Okay, so we'll keep moving on. Okay, so we now start talking about our graphs of gradient functions. Okay, so I've just got a little bit of a table here. So if our given function was linear, okay, then the gradient, okay, function would just be a constant value, where the gradient of the linear graph becomes a y-intercept. Okay, so if this had a gradient of 2, that would be a constant at 2. Okay, if we had a quadratic, then it becomes a linear. Okay, and you'll notice from our work just a minute ago, we're always reducing our power by 1. So that means we're reducing our degree of our function by 1. So a quadratic, when we drop down a degree, it's going to go linear. Okay. Our turning point for the quadratic, okay, is going to become our x-intercept. So our turning point is going to be our x-intercept. And our cubic, okay, is going to become a quadratic. Okay, and our turning points of our cubic, okay, are going to be our x-intercepts of our quadratic. Okay, and we could also say if we're looking at a quartic, okay, then that would become a cubic, and again our turning points of our quartic would be our x-intercepts of our cubic. Okay, we've got a little worked example to do here. So we've got the graph of f of x is shown below on the same set of axes graph f dash of x. Okay, so you can see here, we've got our cubic. We're told that we've got a turning point at negative 2.5 and a turning point at 1.5, negative 6. So all that means is we come down here, and that's going to be an x-intercept. And we come over here, that's going to be an x-intercept. Okay, and now we can draw our function. Okay, without more information, we couldn't tell what our y-intercept is. Okay, we need to know a bit more information than what we've got there. Okay, so basically we're finished that one. There's not much to it. Okay, we'll flip over, keep going. Okay, so just a couple other points on graphing. So our turning points of our original function become the x-intercepts of our derivative. Where our original function has a positive gradient, so that means that we're sloping this way, okay, has a positive gradient, then the derivative will be above the x-axis. Where f of x has a negative gradient, okay, then our derivative will be below the x-axis. For f dash of x to exist, then f of x must be smooth and continuous. So by smooth and continuous, okay, something that's not smooth or continuous, okay, if we have a point, okay, or we have a gap. So not smooth because it's got a point, not continuous because we've got a break in our function. Okay. So equations of tangents and normals. Okay, so our tangent equation is, and it's not really our tangent equation, it's just our equation of a straight line, is y minus y1 equals m outside of x minus x1. So for this, remember m is our gradient, okay, because our equation of our tangent is going to be at a specific point, okay, which is going to be x1, y1, okay, is going to be the point where you're trying to find the tangent, and m is going to be the gradient of the tangent, which we can find from our derivatives. Okay, our equation of our normal, okay, is y minus y1 equals minus 1 over m x take x1. Okay, remember tangents and normals are at right angles to each other. So if we've got a little graph, okay, so if we had that there, that would be our tangent at this point, and this would be our normal. Okay, and they're at right angles to each other. Okay, and we also have the angle of inclination to the horizontal can be found using m equals the tan of theta. So our theta is going to look like this. So if we've got a little graph there, we've got our tangent, then our angle of inclination is going to be from here. Okay, and that's found using our gradient equals tan of theta. Okay, so just got one worked example to go. So we've got the graph of f of x equals 1 minus x outside of x take 3 outside of x take 6 is shown below. Find the equation of the tangent at our spot 4,6 and the angle of inclination, and the equation of the normal at our point 4,6 and the angle of inclination. So we're going to need to actually find our equation of our derivative first. Okay, so the first thing we're going to need to do is expand out these brackets. So now f of x. So when we multiply all those out, just to save a little bit of time, okay, we get that it's minus x cubed plus 10x squared take 27x plus 18. Okay, you could expand on your calculator, you could do it by hand, doesn't matter, you're going to get to this. So our derivative, f dash of x, okay, well, we've got to bring our power down the front. That becomes minus 3x squared plus 20x minus 27. Okay, so we've got our derivative. Now we also need, though, our derivative at x equals 4. So we've got to do f dash of 4 equals minus 3 times 4 squared plus 20 times 4 minus 27. Okay, when you do the work on that, you get that the gradient is equal to 5, or if you like, m is equal to 5. Okay, because we need to do our equation of our tangent and our normal. So our tangent, okay, remember it's y minus y1 equals m outside of x minus x1. Okay, we put everything we have together. So y take 6 equals m, which is 5, okay, outside of x take 4. Yeah, y take 6 equals 5x take 4. So we get y equals 5x plus our 6 plus 2 for that one. Okay, and our angle of inclination, well, that is, we use m equals tan theta. So theta is going to equal inverse tan of m, which in this case is inverse tan of 5. Just see what that gives us, so just give me 2 seconds. Alright, inverse tan of our 5 gives us a theta of 78.7 degrees. Okay, and for our normal, well, it's basically the same process. It's just we have y take y1 equals minus 1 on m x take x1. Okay, so that m is still our gradient at that point. So it's y take, it still takes 6 because we're talking about the same point, equals minus 1 on 5. Okay, x take 4. Okay, so we get y take 6 equals minus x on 5 plus 4 on 5. Y equals minus x on 6 plus 6 and 4/5. Sorry, that should be minus x on 5, not 6. Sorry about that. Okay, and our angle then is this time we've got to do inverse tan, okay, of our gradient, which is negative 1 on 5, equals theta. So theta will equal, 2 seconds, our inverse tan of negative 1 divided by 5 gives us negative 11.3 degrees. Okay, so that just means that we're going to be going down a bit instead. Okay, so that's everything for this section. So there's a little bit to it. As I said, it's a bit of a review though, so hopefully this stuff isn't new, and it's more just a bit of a revision.